What function are you using? Where is it? It's this one.
Oh, yeah, I was like, this really light, right?
Negative.
Then you pulled right. Oh, yeah. That was right behind you. And then you went to the left lane, I went to the right lane. And nobody was like, I was like, wait. I thought it was gonna be your.
Oh, it's the trees are the same.
And then. That was because I was doing.
Ah. So check your excuse first.
All right, let's start with number one. I changed the worksheet 4 just slightly, but doesn't just to so that you guys have these potential distractors and knowing that it doesn't impact your first step, right? We're approaching left, the right, we're always doing direct substitution. It may not even mean anything for our problem, but we don't want to get distracted and start doing decimals if there's no vertical asymptote, but always direct substitution first. Okay, so 0 in for x. We get root 19 minus root 19, that's 0 over, I slightly changed it, my bad. I was doing last minute changes and I forgot to change that. So that's meant to be just x. Let me see, did I make any other mistakes? Okay, that's meant to be just x. So if I plug 0 in, I get 0 over 0. That indicates that there is a hole. And if there's a hole, then we know we just go through our process, multiply by the conjugate. And we know that we're expecting a limit, but the one-side limit has no impact on our problem. Okay, so. We expand out. Combine like terms, 19s cancels out, the x's cancels out, but there's still a 1 left over up top. And now final step, reevaluate our limit, replace 0 into our remaining x's. So we get root 19 plus root 19, which is 2 root 19, but that's in the denominator, so we don't want to make it just 2 root 19 as our answer. It's 1 over 2 root 19. All right, number 2, approaching -3 from the right, but we don't care about that one-side limit. We're just going to do direct substitution, just the -3. And -3, we get 0 over 0. So that confirms, again, there's a hole, limit exists. It's just like a quiz problem. So we know we have to factor. Once we find our common factors, we can reevaluate. There's a 1 left over in the numerator. -3 minus 1 is -4, so 1 over 4. All right, number 4, approaching 0 from the right, but we don't care about that one-sided limit, just 0. We get 1. Oh, we're going to omit 3, 9, and 19. Yeah, there's no absolute value element there. No absolute value, no trig, and no squeeze theorem. Okay, so 0 in for x. Okay, we get 0 over 0. We know this is one of those complex fraction problems. We have to do common denominator. So we're going to step to the side and just work on getting this to combine to be one fraction, which means we got to do common denominator. So our common denominator is going to be x plus 1. This is really a 1 over 1, so nothing to change with the first fraction. The second fraction, though, is missing an x plus 1, so do x plus 1. So we get 1 minus x minus 1 all over x plus 1. which is negative x over x plus 1. So now this is going to replace that numerator portion from our original problem. Let's revisit our problem. Now that we have that upper portion as one fraction, we still want to, we're making progress, but we still want to resolve the complex fraction. So dividing this by x, the same thing as multiplying this by the conjugate of x. The conjugate of x is just 1 over x. X's cancel out. Reevaluate our limit. 0 in for x. So we get negative 1 over 1, which is negative 1. Okay, question so far. Number 5, we're approaching infinity. We don't plug anything in, right? If we see infinity, we're always comparing our highest degrees. And the degrees may not be in order, so we have to go and look at every degree here. So highest degree is 5. Our highest degree denominator is also 5. So we know the limit does exist. The horizontal asymptote does exist. We just take the ratio of the coefficients. So 4 over 2 is just 2. Yes, 100 or negative 100, depending on where you're headed. If it's approaching positive infinity and the degree is higher, then you'll plug in 100. If you're approaching negative infinity and the degree is higher, you'll plug in negative 100.
Okay.
Yeah, plus and minus, because you're only deciding between two options. It's either positive or negative infinity.
Okay.
Is that
0. Yeah. Yeah, there's only 3 options if you see infinity. It's either 0, ratio, or plus or minus infinity. All right, number 6, limit as x approaches infinity. Again, we have infinity, but here, looks like we have different families of functions here. I'm going to resolve that negative x. Maybe I can see things a bit more clearly if I bring that negative exponent into a positive exponent. This is more clear now, right? These are not the same types of functions, but relationally, we know that there's a certain order, right? This falls under comparative growth rates, where logs is slowest, followed by radicals, followed by polynomial, followed by exponential. So if we categorize it, numerator falls under what category? Polynomial. Denominator is exponential. So I have a slower function up top. I have a faster function below, which means that my fraction is going to approach what? 0. If it was faster over slower, then you know it's either plus or minus infinity, and then you'll just test 100 to see which signs you're going to get. Okay, questions so far? All right, number 7. It's another one-side limit, but we never want to skip our first step. So we always are going to just plug in the integer value, or yeah. So negative 3 in for x. That's negative 3 squared, which is 9. 9 plus 3 is 12. So 12 over 0. So now this is indicating to us something, right? This means what? Vertical asymptote. The full limit doesn't exist, but it's only asking about the approach from the left of the asymptote. So it's either doing one of two things, right? Either going to go up to positive infinity or it's going to go down to negative infinity. So this is where we test decimals. What's a decimal to the left of negative 3? So numerator, I get positive. Denominator, I get negative. Positive over negative is negative. So we know the graph is headed in this direction.
What if it was just saying as soon as x approaches -3?
Then I would just stop and say limit doesn't exist. And it's a vertical asymptote, but you first have to confirm it's a vertical asymptote. That's right. That's right.
It's like, she said, it's just x approaches -3. Wouldn't you have to simplify it too? And see what?
Remember, if it's 12 over 0, there's no factors, right? If it's 0 over 0, then you're expecting a factor. Then you move forward and try to cancel out a whole. But if it's 12 over 0, there's nothing that you're going to find that can factor or that can match. Good. Any other questions? All right, number 8, first things first, direct substitution. We get 1 in for x. We get 1 plus 2 plus 1, which is 4. 4 over 0. Again, there's a vertical asymptote, same scenario. Limit doesn't exist, but it's only asking about the movement of the graph from the right side of 1. So it's either doing one of these two things. You don't have to draw this out. I'm just drawing this to help you see how the graph what the graph is doing around that region. It's one of these two options. So we'll test the decimal. What decimal can we test? 1.1. So I'm not going to do all that, but we understand, okay, everything is positive here, so that's just positive. 1.1 minus 1, that's also positive, so therefore positive. Okay, we're skipping 9. Okay, we're supporting our answer with continuity conditions. We're basically trying to figure out what is the b value that will allow this function to be continuous. So our first condition is our point. We know that our problem is centered around that -6. So we'll say f of -6 equals b. We're just gathering information, nothing conclusive yet. Second condition, we want to find limits, and we know that the limit is looking at the graph, and we know that this is just a point, so we're not going to look at the point. But we only need one limit statement because less than and greater than, it's all contained within that restriction there. So everything to the left, everything to the right of -6. So all we need is one limit statement, and it's just with the first piecewise function. So we get 36 minus 48, which is -12. -12 plus 12 is 0. So we get 0 over 0. We know there's a hole, so we keep going. And factor multiplies to be 12, adds it to be 8. Reevaluate our limits, replace -6 in for x, and we get -4. So limit exists. We keep going. We haven't found what the b value is, but now it's obvious that by the third condition, we need the first two to agree. We want continuity, so we're forcing every condition to be true. If we want the third condition to be true, b must be equal to -4, and we have our b value. Okay. 11 through 18. If you have any questions about these.
When it's approaching, I can it be 2. Since it's not coming from like the left or the right.
Remember, if we want to find the limits, we start off by picking points on both sides of 1. So I'm picking from both sides of 1. I'm going to follow the path of my graph and create arrows, right? We always want to create arrows and ask, are the arrows pointing to the same y value? If they are pointing to the same y value, then the limit doesn't exist. So we're always looking for arrows. If you're looking at a point, there's no arrows they can create. There's nothing they can pick on either side of that point. So never look at the points if you're finding limits.
With 17, that would be the point.
That's right. 17 is just a point. Yeah. If you see limits, draw your arrows. If you see a ordered pair, then we don't care what's around that point. Just find that point. Okay, good. Anything else, 11 through 18? All right, 14, f of -2. So we want to find the order pair at -2. There's a hole here. We don't look at that. There's an order. There's a filled in point here. So f of -2 is just going to be -2. Yeah, remember, hole means that your graph gets closer to that point, but it never reaches that point. Remember, this is asking what is the one-sided limit. So it's basically asking create an arrow, but just create an arrow from the left side of -2. So this tells us we need to start off with a point from the left side of -2, which is, I'm just going to pick a point here, and I have to move towards -2. And the one-side limit is it's just asking what is the movement of just that left arrow. That's right. Yeah, it can be a fill in circle because it's just the approach, right? It could be a hole, it could be a point. It's just we're not looking at what that point's doing. We're looking at what the arrow's doing, right? The arrow's headed towards that point, so that's enough for our one-side limit, even if that point is not filled in. Good. Any other questions? Okay, we skipped 19. All right, 20, identify each type of discontinuity. So we know discontinuity comes from the denominator. So if we factor everything out, we can see what's going on. So if I factor the denominator, I get x minus 5, x plus 3. We know that any factor that does not cancel out must be the location of a hole. Sorry, location of a vertical asymptote. Any factors that do cancel out, we know that's the location of a hole. So we know there's a vertical asymptote at x equals 5. Vertical asymptote, it falls into the category of a non-removable discontinuity. And then a hole is at the point negative. Basically, you're just finding the limit. If I plug -3 into the reduced expression, I get -1/8. Yeah, the limit is the location of the y value location of the hole. And that is a removable discontinuity. So non-removable is a vertical asymptote. This means that there's nothing that we can't just make one change and all of a sudden the function is continuous. So if I had a graph that looked like this, I can't make one single change and make the function continuous because there's too much of a gap here. But if it's removable discontinuity, then there's a hole in the graph. Maybe the graph looks like this, right? But we're 1 point away from achieving continuity, so we're able to remove that discontinuity just by making one change. That's the difference. Yeah. That's non-removable. Yeah.
Are there any other like factors that like play a role?
Just the denominator, right? Make sure that, let's say there was an x plus 2 up here. We don't look at that. That's an x-intercept. X-intercept has no, it's your discontinuities only come from the denominator. So if it doesn't show up in the denominator, then it is not a break in the graph. All right, 21. Identify all horizontal asymptotes. We know that this is one of those potentially strange functions that have split asymptotes. So let's just look at how the graph is looking like on one side. And for approaching infinity, what do we do? Yeah, compare degrees, right? What's the degree of the numerator? 3, yeah, because this is square root of 6, right? Square root of x of 6, which is x cubed, x cubed, the degrees match. So
If you like something,
Mhm.
you just divide the x
by 2.
by 2.
Mhm. Yeah.
Maybe it's like x to the 8.
It'll be x fourth, yeah, because you know that we know that square root of x to the 8th is x to the 4th, because x to the 4th times x to the 4th is x to the, it's half of x to the 8th. All right, so what's the ratio of the coefficients here? Root 16 over 5, right, which is 4 over 5. Now, this is one of them, right? But we know that if we're approaching negative infinity, what's going to happen? There's going to be what that's going to show up? Negative 4/5. Yeah. So really, if you see the scenario where, okay, I got a radical, my degrees are the same, there's always going to be two asymptotes. So you're going to write y equals 4/5 and y equals negative 4/5. If you find one ratio, it's the same ratio on the other side, just a different sign. You don't have to show all this work. You can, if you want to jump directly to this conclusion, just make sure you call them y equals then, since we're asking for horizontal asymptotes. Yeah. I'm sorry, say it again. This is a little bit strange in terms of this is not quite a radical because this can kind of clean up to be an x cubed. Like a radical would be more like square root of x if it was just square root of x like that. Yeah, if it was like square root of x to the 6, that's really falling into the category of x cubed. So yeah, you're not gonna, if I ask you a question, it'll be asking for horizontal asymptotes. I won't set up the problem like this. If it was comparative growth rates, it'll be more like this. It'll be, yeah, I see what you're saying. Yeah, this is more comparative growth rates because this is clearly just the square root of x. This is x cubed, so now it'll be radical over a polynomial and 0. Yeah. All right, a big piecewise function here, number 22. All right, limit as x approaches negative infinity. Which one do we choose? That one, yep. Okay, what do we do when we see positive or negative infinity? Compare degrees, right? Degrees, degree 1, they have the same degree. We take the ratio of the coefficients. All right, 2 from the left. Which one do we choose here? Still the first one. All right, first things first. Just plug in just 2, right? Just 2. Okay. What does that tell us? Vertical asymptote, the limit doesn't exist, but it's only asking of the approach of that asymptote from the left side. So now we can use what? Decimals. And you'll test what? Okay, so numerator get positive. 2 times 1.9 is slightly less than 4. So like 3 point something minus 4, that's negative. Okay, 2 from the right. Third one here, right? Right, 2 in for x, no decimals, right? Just the integer. So 4 minus 5 is -1. That's a real number. There's nothing more that we need to do. Okay, limit as x approaches 2 doesn't exist, right? The point has no say on what the limit is. We see the graph split on either side of 2. We need to look at how the graph is behaving from both sides of 2. They're obviously not pointing towards the same y value, therefore the limit doesn't exist. If these were both, let's say these are both headed towards -1, then your limit will be -1. So what that would look like would be the graph could look like this. Both sides are headed towards -1, but the point is sitting up here. It's not continuous, but what would you say the limit is? Would you say that point, or would you say the whole? The whole. Right. So again, the limit is about the approach. The point is just an island. It doesn't have any say on what the limit is. Okay. But yeah, this one does not exist. Okay, approaching 5 from the left. All right, 5 from the left. Which one do we choose here? 6 minus 5, right? Slightly to the left of 5. Direct substitution. 10 minus 5 is just 5. Limit as x approaches 5 from the right. Last one. Direct substitution first. We get -25 plus 4, which is -21. Okay. That indicates to us there's a vertical asymptote. We're approaching an asymptote from the right side. 5.1. Negative over a negative. Limit as x approaches 5. Doesn't exist, right? The order pair is at a different location, but we're asking for the limit, not the order pair here. So 3 from the right. That falls into that category between 2 and 5. So we just use that 2x minus 5. Direct substitution. 6 minus 5 is 1. Finally, limit as x approaches infinity. Last one here. All right, what's our first thing that we do if we see infinity? Compare degrees, right? What do we see? Top is higher, which means that it's either one or two things, right? It's going to either be positive infinity or it's negative infinity. And then to decide between these two, we can now use what? Now we can test the number, right? Test in the direction that we're headed. We're moving right. We're headed towards the positive infinity. We'll choose a large number on the positive side. So we'll test 100. Okay, numerator is negative. Denominator is also negative. So positive infinity. Questions? All right, next up, 23. Sketching your graph. I'll show my version. Let me know if you have any questions. Remember, for f, if a limit doesn't exist, you can do a lot of different things here. You can make it a jump discontinuity. You can make it an endpoint. You can make it a vertical asymptote. So it doesn't have to look like what I have here. Okay. Any questions with the graph? Okay, 24. Find the value of k that makes a function continuous. So we're just going to walk through continuity conditions, make every statement true, and then before we know it, we're going to be able to solve for k. So first things first is the order pair. So we know -2 is defined with the first piecewise. So plug -2 in for x, we get 2 times -2 plus k, which is -4 plus k. Mm-hmm. Oh, you mean right here? Wait, hold on. Actually, 3 from the right is equal to 5. Where do you see a horizontal asymptote? Here it says the limit doesn't exist. So that could either be a jump discontinuity, it can be a vertical asymptote. It's up to you. It doesn't, but it's not a horizontal asymptote. It's a vertical. I mean, it can be a vertical asymptote.
For E, they have to go the same direction. Going up, down.
They both need to go up because that infinity is telling us the behavior from both sides. Yeah, so we do need to see both arrows pointing up.
Yeah.
That's right. Yeah, if it was like -2 from the left side of -2, then that means I only need to commit to that left side going up. I don't have to do, unless there's another statement telling me what's happening on the right side, I don't have to show that right side. You can, yeah. You can show more than what the characteristics are asking you to do, as long as it doesn't conflict with other statements. Okay, anything else with the graph? Okay, so back to 24, we have the order pair. Second condition is, does the limit exist? We have a less than and greater than, so we have to spend the time to find the one-sided limit. So set up our one-sided limits, approaching -2 from the left, approaching -2 from the right. Find the appropriate expressions, replace every x with -2. And we have our one-sided limits. It's still unresolved, but we know we can set them equal to each other because we want continuity. So that means the one-sided limits have to be in agreement. And if they have to be in agreement, we can set them equal to each other. And when we solve for k, then we have our answer, right? We're just using continuity condition to help us get to our variable. And once we have it, we can stop. There's nothing more that we need to do. We don't have to show any other conditions. Uh, if we have f of x, we're not able to get the exact value. So this is a more specific way of plugging that value in. Because we need to know what the values are. So this is f of x split up on either side of -2. Are you asking about the third condition or
No, I'm asking about
condition, right? So remember, for one-sided limit, we have to plug in, find the appropriate piecewise function, and then plug in, right? Uh, I see what you're saying. I mean, I think I see where that because that's the way that we did it over here, right? We were always setting it equal to each other. But the thing is, we don't know what it's equal to yet. We have to plug in to find out what that value is.
okay, see.
Right. Yeah. Um, I want to see if I can clarify something here. Let's say this one here, right? Limit as x approaches 5 from the left of 5 of f of x equals 5. We can say that over here, but we don't know what f of x is yet. We actually have to find that piecewise function, plug it in before we can confirm that it's equal to 5. So this is still unresolved. We have to be able to use the expression to find what the limit is. So yeah, so we always have to plug in, unless they give us what the limit value is, which in this case, in these types of problems, they're not going to give you what the limit is. You're going to have to find it yourself. You always have to plug in. Okay, are we okay with 24? Yeah, let's do 24.
Right. Like, but what if we get a question right with the writing?
Then you might lose a point. Yeah, I'll go over that. I mean, to earn full credit for 25, we do need to have statements about continuity. We need to have the justification, and we need to be able to write out the statement.
Okay.
But it's not all or nothing. So but let's go over it and see if you have any questions about the writing. And this is not the only way to write the justification. This is just the most efficient way using the least number of words. Okay. but I'll read your statement and see if it has all the pieces. So here's 25. Verify that intermediate value theorem applies for our function x squared plus x over x minus 1 between 2.5 and 4 for f of c equals 6. So the big picture here is we want to know if our graph is going to pass through a y value of 6. But we're forcing ourselves to use very limited information. We don't have the graph in front of us. We're just using continuity and if the endpoints are above and below our target. That's all we have to work with. And if it fails any of those things, then we have to stop the problem and say IVT doesn't apply. Okay, but if it passes all three conditions, then we know our graph is going to be guaranteed to cross the y value of 6. Okay, so that's really the big picture. Okay, so first things first is we want to know if there's any continuity issues on our function. So where do we look for discontinuities or continuity issues? In the denominator, right? So we look at the denominator and we ask, where is our discontinuity? At x equals 1, right? There's in this case, there's a vertical asymptote, but we really don't have to categorize. If it's a hole or an asymptote, there's a discontinuity, but there's a vertical asymptote at x equals 1. Now, we have to ask, is this discontinuity going to impact or interfere with my interval? No, so we're safe, right? This is the only discontinuity. It is safely outside our interval. Our interval is safe. Our function is continuous on a closed interval. So we can go ahead and make that statement.
If it doesn't, you have to remove.
No, if let's say this is x equals 3. If 3 is between the interval, then we stop the problem. Function is not continuous. IVT doesn't apply.
Okay. And then would you say?
No, you just have to, it doesn't matter. Yeah, if it's not continuous, it could be a hole or an asymptote. If it's not continuous, there's no, we don't go past this point. We stop the problem and we can't go any further. Okay, our function is continuous though. Okay, so now we have to depend on the y values. But right now there's a mismatch, right? These are y values, these are x values. We need to get them to be the same variables. So we're going to plug 5/2 into the function, and we'll plug 4 into the function. Again, sorry if these numbers are hard. You're going to get easier function to plug in, so you don't have to worry about, getting difficult or having to do difficult calculations to figure out what that decimal value is since you don't have a calculator. But let's say we plug 2.5 into, I'm just going to do the work for us. Ends up being 35 over 6, which is around, I'm sorry. Oh, sorry, 2 point. This just reduces down to this fraction if we were to plug in the calculator. It's a decimal over a decimal, and it just reduces to be 35 over 6. So let me show you what the calculator shows me. Sorry, I'm skipping some steps here. It's 8.75 over 8.75 divided by 1.5 gives us 5.83. And if I convert that into a fraction, it's 35 over 6. But you don't have to worry about doing these messy decimals on the test. Okay. But it ends up being around 5.8. That's what I want us to know. Okay, f of 4. Okay, so let's just say that we're able to get to these numbers. Is this going to pass IVT? We're starting at a y value of 5.8. we're ending up at a y value 6.7, and the graph is continuous on this interval, it's got to pass y equals 6 somewhere between. Okay, so we're guaranteed it. We know that our our graph is going to hit that target y value. So now we can focus on writing our justification. So we can say by IVT, and we just have to show that we're comparing these numbers, but we're also involving the endpoints. So I'm going to start with the lower y value. Since one endpoint is showing me 35/6, which is 5.8, which is clearly below my target y value of 6. And that target y value 6 is clearly below my other target y value, which is 20/3, which is coming from f of 4. There must be a c value where our target y value is equal to 6, somewhere on the interval from 2.5 to 4. So now that we're guaranteed that this graph is going to have this y value of 6 somewhere on the interval, now it's asking to see what is the x value location of that order pair where this occurs. So how can I find that c value? Yeah, we know what the y value is. We're just using the function now to figure out what the x value is. So I force a 1 in the denominator here so I can match my diagonals and pair up and cross multiply and solve for x. We got to bring everything over to one side and go through our factoring steps. So we have two candidates for c values, c equals 2 and c equals 3. But are both of these valid? What's the issue? Yeah, we only care about an order pair that lives on the interval. If it's outside the interval, then that's not part of our problem. So which one do we remove? Two, right? Because 2 is clearly not between 2.5 and 4, but we're guaranteed to find at least 1, and we have 1 here. Okay, let me know if you have any questions. Yes, we can either put this within the statement or just have it somewhere.
Yeah.
I'm pretty sure it's like a first all second. So basically what we do is reference on yeah. No, but it doesn't matter. All that's not saying that. So it's the no X. I mean the Y values. So whatever I'm trying to find. So then there has to be one that's yeah. So then you put the whole statement there as well. And then you find the X value of 6. You find the C value. Yeah, so where there's the X. Yeah. Yeah. No, I know, but like. Yeah, I just want that.
Make sure you say
Well, I'd like to go to you should. Yeah, and like there's like, I have like a bunch of.
Yeah, so like, if it's like say you have like this vertical system, it says like, what is that? Like f of -2 equals like 5. You can put a really big there, put a little bit.
Okay, so it doesn't matter. Who it's actually like it should. It's a pride was like. No, I was.
Actually say white. And then these use. No, you can say this.
Oh, pretty gay. When was like, what is removals?
So reverse continuity would be if the third condition fails, which means that the hole is not getting filled in.
But how would, because how would the third condition, like, what is that's like considering the removals?
I feel fine.
Right, but it's careful that you're writing. And if the second condition fails, there's no need to look at the passes.
Okay.
So let's say it was this.
She forgot about it.
Really?
And she was trying to give us another. And so.
Let's say up to.
Okay.
And let's say there's a piecewise function and you plugged in, and you did all the work. You got this equal to 4.
Okay.
And then you plugged in from the right. And then you also got 4. So this passes, which means that the full limit does exist.
Okay,
So non-removables, the limit doesn't
all you have
pass,
to
and then.
No. That's right. Non-removable is the limit doesn't pass, but the limit passes, but as a third condition, there's an issue here.
It's continuous, so then you look at the.
If
denominator.
this occurs,
So it's like x minus 1, then that means that's a
Yeah.
removable output.
then this is removable this time.
Okay.
But
Thank you.
like, let's say it's 5 over 2 to 4, that doesn't affect it, so it is continuous between that interval.
Nice.
I love those numbers, and then you're gonna try to get a number that's gonna range between 6. Like, do you know what I mean? And then all you have to do is plug in 6 as f(x) and then call out the find c. Does that make sense? When it's kind of hard without reachable already. Do you have to go all condition? Yeah. Or it's makes sense. It's just gonna end the call. So it's gonna be like, read the x, that's exponential, or it's gonna be like the x to the third, and that's gonna be. It's like, element.
Don't you?
And with that moment, you sorry, figure out if it's slower over the top, and that's 0. If it's faster or slow, it's faster.
Yeah. So say at the back, I would. So that you can grandfather that.
Sorry, can you hear about what?
Yeah.
No, I was there, it's like.
I know, it works for me, it's like, they're not, they're.
That was actually the original. So that's all.
Oh, that's so sad.
Number one is plug one. And now it's going for so this is to
Like, why that? Yeah. No.
There's gonna be y'all, because like, the teams are really.
No, it's same thing.
I know their faces and I know some. No, oh, that's what I said. Correction.
Yes, for that one, I'm gonna say don't. But everything else. I think all your book bags up in the front, all your phones up on the wall.
We're holding both of them. This is so sweet to see.
I know, I went like in the class and I'm like.
I'm gonna say, I'm like, it's a little part of my.
Thank you. Yeah.
So you go through continuity conditions and then you go through. There, I'll pass on the test first. And then I just
Yeah, and I'm. It's like more than. When I finish watching it. Like, this, you're gonna get on. Like, I told her, you don't care. Like, after, like, your kids' customers or your business. Like, when you take this. My brother. What? No, I don't need it then. I took my photos yesterday. Oh, it was yesterday. Yeah, no, you're good. I make sense. Texted me, I was like, while you're in right now, ask back to come in your house. She goes, what the heck are you talking about? I was like, just give me the garage. And then I scanned it, just that, he's like, honey, how are you doing? I was like, I'm just grabbing this thing. No, I grabbed something. I went yesterday and I got my stuff. And then I got, I just my fingers. It works out.
Yeah, we got.
And then I'm taking you off to that. Yeah.
Sorry. Yes. I'll be on board.
Today's 28th. Take a new continuity conditions. First condition is order pair. So to your function. See what you get. Second condition. Does the limit exist? There's less than greater than. So I'm going to do 2 on side. So I do things 2 on the left. So get the first case once. But negative 2.
X, negative 4 plus k, still can resolve, right? Just see what else happened. On the right side of the 2. K x minus 3, like that, and then 2k minus 3. And one continuity is finding both these statements to be I need the arrows to go in 3. So I just set them equal to each other. And I solve the k plus k. Seems like.